In this video, we'll learn the basic concept of binomial theorem. The binomial theorem tells us how we can expand a binomial to the power of n. In junior forms, we have already learned that a plus b squared can be expanded as a squared plus 2ab plus b squared. Then for a plus b to the power 3, it can be treated as a plus b squared times a plus b. In other words, that is a times a squared plus 2ab plus b squared plus b times a squared plus 2ab plus b squared. After further expansion and simplification, we can get that the result is a to the power 3 plus 3a squared b plus 3ab squared plus b to the power 3. Then similarly, we can do the expansion for a plus b to the power 4 because it is just a plus b to the power 3 times a plus b. And therefore we can get that it is equal to a times a cubed plus 3a squared b plus 3ab squared plus b cubed plus b times a cubed plus 3a squared b plus 3ab squared plus b cubed. After that, we should know that a plus b to the power 4 is equal to a to the power 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the power 4. Although we know that we can always do the binomial expansion in this way, yet this kind of expansion is extremely time-consuming. Now we want to figure out if there is any pattern that can help us to do the expansion in a more effective way. From this result, first of all we can observe this. For the expansion of the power 2, the terms that we obtained are all degree 2 terms. These are all the degree 2 terms involving the variables a and b, and there are 3 such terms. For the expansion of the power 3, the terms that we obtained are all degree 3 terms, and there are 4 such terms. Similarly, for the expansion of the power 4, all the terms that we obtained are degree 4 terms, and there are 5 such terms. From this observation, we can see that it is easy for us to list all the terms of a binomial expansion. And now the only question is, how can we obtain the coefficients? In order to help us to observe the pattern of the coefficients, now we let a plus b to the power 4 be c0a to the power 4 plus c1a cubed b plus c2a squared b squared plus c3ab cubed plus c4b to the power 4. And see how the coefficients of a plus b to the power 5 can be calculated in terms of c0, c1, c2, c3, and c4. Now we can see that a plus b to the power 5 can be expanded in this way. In descending powers of a, the first term in this expansion should be a to the power 5, and it is obtained by a times c0 a to the power 4. And then the second degree 5 term should be a to the power 4 times b, and it is obtained by a times c1 a cubed b plus b times c0 a to the power 4. Similarly, we can get the terms a cubed b squared, a squared b cubed, ab to the power 4, and b to the power 5. Now we can see that there is a very nice pattern that for the coefficients of the degree 5 expansion, they can be calculated by the sum of the consecutive coefficients in the degree 4 expansion. On the other hand, we can see that the first and the last coefficients are always 1. And therefore a plus b to the power 5 is equal to a to the power 5 plus 5a to the power 4b plus 10a cubed b squared plus 10a squared b cubed plus 5ab to the power 4 plus b to the power 5. Following this pattern of adding up the consecutive coefficients, we can also expand a plus b to the power 6. To do this expansion, first of all we just need to list all the degree 6 terms involving a and b. And then we refer to the coefficients of the expansion of power 5, and we know that the first and the last coefficients are 1. Now for the coefficients in between, they are just the sum of the 2 consecutive coefficients in the degree 5 expansion. As a result, we can expand a plus b to the power 6 very quickly. Similarly, to expand a plus b to the power 7, we just need to refer to the coefficients of a plus b to the power 6, and then we do the same trick of adding up the 2 consecutive coefficients. Now if we consider all the coefficients that we obtained by expanding a plus b to the power n in descending powers of a, And if we include a plus b to the power 0 and a plus b to the power 1, then all these coefficients can be written in the form of a triangle. In mathematics, this triangle of binomial coefficients is called the Pascal's triangle. Now let's see how we can obtain the coefficients of the degree 8 expansion. First of all, we know that the first and the last coefficients are always 1. And then for the coefficients in between, we just add up all the 2 consecutive coefficients in the previous row. Sometimes it is useful to know that the numbers in the Pascal's triangle are symmetrical. It implies that actually we just need to calculate the first half of the coefficients, and then for the coefficients in the second half, they are just the same as the ones in the first half. Now we can expand a plus b to the power 8 very quickly by copying the coefficients and presenting the terms in descending powers of a. Using the Pascal's triangle is a good way to calculate the binomial coefficients, but it is still quite time-consuming if the power is very large. Now we want to look for an even more direct way to calculate the binomial coefficients. Let's take a look at a plus b to the power 4 as an example and see how we can calculate the coefficients of 4, 6, and 4 in a more direct way. A plus b to the power 4 is the same as a plus b times a plus b times a plus b times a plus b. And we know that the multiplication of these 4 brackets can result in the terms of a to the power 4, a cubed b, a squared b squared, ab cubed, and b to the power 4. In order to result in the term a cubed b, the first way to do so is to take out b in the first bracket, and then we multiply the 3 a's in the second, third, and the fourth bracket. Or we can take the b in the second bracket, and then we multiply the a's in the first, third, and the fourth bracket. Or we can get the b from the third bracket, and then get the a's from the other brackets. Or we can get the b in the fourth bracket and then get the a's from the other brackets. In other words, there are 4 C1 ways to result in a cubed times b, and therefore the coefficient of this term in the expansion is exactly 4C1. Similarly, to obtain the a squared b squared, the first way to do so is to take the b's from the first and the second bracket, and then we multiply to the a's in the third and the fourth bracket. And the second way to do so is to take the b from the first and the third bracket and the a from the other brackets. The third way is to take the b's from the first and the last bracket and then the a's from the other brackets. The fourth way is to take the b from the second and third brackets and then the a's from the other brackets. The fifth way is to take the b from the second and the fourth brackets and then the a's from the other brackets. And then the sixth way is to take the b's from the third and the fourth bracket and then the a's from the other brackets. In other words, there are 4 C2 ways to result in a squared b squared, and therefore the coefficient is 4C2. And then for the term ab cubed, the first way to result in this is to choose the b's from the first 3 brackets and then choose the a from the last bracket. Or we can get the b's from the first, second, and the last bracket and then a from the third bracket. Or we can get the b's from the first, third, and the last bracket and then the a from the second bracket. Or we can get the b's from the second, third, and the last bracket and then get the a from the first bracket. As a result, there are 4 C3 ways to result in AB cubed, and therefore its coefficient is 4C3. Now to complete this pattern of the binomial coefficients, we can write 4C0 and 4C4 here, because we know that these two values are equal to 1. From this nice pattern of binomial coefficients, we can see that we can actually expand a plus b to the power n by considering the combination NCR. And we can actually rewrite this expression by the summation notation like this. That means very straightforwardly, for n to be a positive integer, a plus b to the power n is just equal to the sum of NCR times a to the power n minus r times b to the power r, where r is from 0 to n. By considering that NCR is equal to n factorial over n minus r factorial times r factorial, all the binomial coefficients can be calculated directly. This useful result is what we call the binomial theorem in this video. If we consider the Pascal's triangle together with the binomial theorem, we can obtain the Pascal triangle in terms of NCR. From this special version of the Pascal's triangle, we can observe some properties of combinations. Since the numbers in the Pascal's triangle are always symmetrical, we can see that NCR is always equal to NCn minus r. For example, 4C1 is equal to 4C3. On the other hand, since the numbers in the Pascal's triangle are obtained by adding up the consecutive coefficients from the last row, we can conclude that NCR plus NCR plus 1 is always equal to n plus 1 CR plus 1. For example, 3C1 plus 3C2 is equal to 4C2. This is the basic concept of the binomial theorem. Lastly, let's quickly take a look at how we can apply the binomial theorem to do the following expansions. For 1 plus x to the power 6, we just need to calculate the coefficients by considering 6CR, where r is from 0 to 6. And 1 to the power of anything is still 1, and therefore the result is like this. Then for 3x minus 1 to the power 3, we can treat that it is equal to 3x plus minus 1 to the power 3. That means the a in the binomial theorem is 3x, and the b in the binomial theorem is minus 1. As a result, it is equal to 27x to the power 3 minus 27x squared plus 9x minus 1. For the last one, 2a squared minus b to the power 4, similarly it can be treated as 2a squared plus minus b to the power 4. Therefore, by the binomial theorem, it can be expanded in this way. After simplifying all the terms, we can get that the result is 16a to the power 8 minus 32a to the power 6b plus 24a to the power 4b squared minus 8a squared b cubed plus b to the power 4. This is the basic application of the binomial theorem to do binomial expansions.